it is. Today we're talking about, welcome to the program, and today we're talking about ground fault circuit interrupters. Thanks for joining, and please use the chat session, ask questions, and also on YouTube, use the chat session there too, the comment section. I believe you have to be logged into YouTube to get that done. So let's talk about GFCIs. Ground fault circuit interrupters are, if I look at the National Electrical Code in Article 100, I get the definitions for a GFCI. Basically, a GFCI is a device that's out there to protect us from shock, from coming into accidental contact for shock, and it's a life safety type of device, right? That is there to help prevent the heart from going into defibrillation. It's going to prevent a healthy heart, a healthy individual, from succumbing to shock. So the first thing, before I get into the program, what I'm going to do now is I want to cover our quiz. I don't know if you guys like this as much as I do, but I like to see the results. So I'm going to now cover the results of our quiz. All right, the maximum threshold for a GFCI is? Oh, that's the wrong one. Sorry about that. Got to go back. Now you're going to see the back end of Mentimeter. You'll see all my presentations. I got to go to 2020-04-01 GFCI and the NEC. Here we go. Do show presentation. Whew, I got nervous there for a minute. Here we go. So web training 04-01 2020. The maximum threshold for a GFCI. We had 76 say 5 milliamps, 71 say 6 milliamps, and 25 say 4 milliamps. So whenever we talk about GFCIs, the threshold is a range typically. 5 milliamps is what all of the research, and we'll talk about the research, but 5 milliamps was the number that that everybody uses for protecting from a protection perspective. But the standard UL 943 tells us we have to trip anywhere between 4 to 6 milliamps. So the upper limit is really 6 milliamps. The lower trigger threshold is 4 milliamps. So I have that margin. I could trip anywhere in that threshold. And one of the other questions I didn't ask, but which should have, is if I'm on a GFCI circuit, a lot of people erroneously think that if I come in contact with a conductor and it's say a 120 volt circuit and I touch this conductor, that if I'm on a GFCI I'll only see 4 to 6 milliamps flowing through my body, and that is not correct. What the GFCI trigger threshold means is that anything above 4 to 6 milliamps is going to set this off. If you come in contact with a conductor or something that is energized and current flows through your body, you could see an amp, you could see 2 amps, you could see 30 milliamps, you could see 100 milliamps. The only thing that GFCI is going to do is reduce the amount of time the current flows through the body. It doesn't limit the amount of current that passes through your body. So we're going to learn a little bit more about that as we go through that. But that's sort of, so you guys are split a little bit on that, which is good. This is all learning experience. See, and it's really cool is you can go online as I'm looking at this. So if you go to menti.com and go to 129781, you can actually put in your information, which I just saw the number go up. So people are doing that. All right, the UL standard for a GFCI product is 1053, 940. So the I don't knows, I'm glad you're here. And you might wonder, why the heck do I need to know what the standard is? And I'll explain that to you, because I think that anytime we're looking at a product, there's been some confusion on GFCI and GFPE. So the challenge is, we always call things ground fault. Go give me that ground fault protector. Or go give me GF or GFI. I've heard the acronym GFI. GFCI is a UL 943 device. So 72 of you got that right. UL 1053 is ground fault protection of equipment. And UL 489 is the UL standard for a circuit breaker. UL 1699 is the UL standard for AFCIs. So those are important to understand. And I see you lost my audio. Is anybody else losing my audio here? I want to make sure people can hear me. Let me know if you can't hear me on the chat. All right. So, okay. So those are the standards. UL 943 is the standard that you're looking at for GFCIs. All right. So now this one, which is an outlet. Okay. The reason I put this in there, and I've already gotten a couple phone calls on this one, and some emails. Thank you, Hiram. So I said which one is an outlet, and technically you could say every one of those is an outlet because but two of those are receptacle outlets, but only one of those is just an outlet. You would put a receptacle outlet in an outlet, and the reason understanding this is important is because when you look at the requirements for GFCIs in the National Electrical Code, you will see some comments saying receptacle outlets, and you will see some comments say just outlet, where you say you have a requirement that says you have to have a protection on this outlet, or you have to GFCI protect this receptacle outlet. Those two are different, and it's important to understand the difference because if you're talking about providing protection for GFCI protection for a receptacle outlet, you're talking about a specific either option 1 or option 3. Any outlet, which you see in option 2, any outlet that has a receptacle in it is now a receptacle outlet. If there's an outlet, which is in option 2, that has a light fixture in it, it's a lighting outlet. So you have to understand the terminology and how that term is used in the NEC because some of the requirements will say either receptacle outlet or outlet, and there are some recent changes in the NEC that will demand you understand that. So I guess you could call that somewhat of it's a goofed up question on my part, but I got my point across, didn't I? What is the maximum threshold for a UL 1053 ground fault device? This is a good one. 1053 is ground fault protection of equipment. We've got 6 milliamps. Now those 29 are thinking GFCIs, not GFPE. Remember, a 1053 device is ground fault protection of equipment. I've got 30 milliamps, and that's, I'll tell you what, years ago, that's what I would have said too, because in my mind, every GFPE device was a 30 milliamp device. I have 100 milliamps. 7 people say 100 milliamps because you know why? They probably are thinking about Article 555 because we introduced in Article 555 requirements in marinas that talk about 100 milliamp GFPE. None of these, and I don't know. So the 29 who said none of these, you're in the right ballpark. Now, I didn't ask you why it's none of those, but I'll tell you. When you're dealing with a UL 1053 ground fault protection of equipment, and I did say ground fault device, I should have said ground fault protection of equipment, so error on my part. Ground fault protection of equipment, the pickup points are set by the manufacturer. So if I'm selling a ground fault protection of equipment circuit breaker, or I'm setting a relay, I'm going to tell you here is the response. Here's the pickup points, the trigger points, and then UL standard tells me how long I have to respond. But it's important to remember, ground fault protection of equipment is there for equipment protection. So the right answer to this is none of these because it's really defined by the manufacturer, and you can have a GFPD, a ground fault protection of equipment device that is set to trigger at 30 milliamps, A GFPE device is set to trigger at 50 milliamps, and there's nothing in the National Electrical Code that says it has to be one of those, except for in Article 555, we introduced the 100 milliamp threshold, that does tell you it's GFPE, but it doesn't mean that that's what the standard calls out. Okay. We still have excellent connections. What is the let go threshold for a healthy male? All right, so we've got 30, 40, 75, and not sure. 30 milliamps is the answer there, and I have a slide in this slide deck that talks about this specific thing, but I'll let you know that let go is just around 30 milliamps, and we'll talk about that a little bit later. And I know Nihad El Sharif is on the line. Maybe when we get to that slide, I might ask him if he's available to comment on it, but we'll move forward for now. A GFCI is your first level of defense against shock. I got 76 say true and 100 say false. 2 don't know. Well, let me tell you. Let me ask this: when you get in the car, do you drive like that airbag is your first level of defense from an accident? Is that how you drive? I mean, if you're in maybe the guys in New York City, or I know there's some people in Pittsburgh, Pennsylvania. I've been on the roads with them, but that's not typically how we drive. We practice defensive driving because the airbag is really the last level of defense against an accident. So your GFCIs, we don't work and we don't operate like hey, I've got GFCI, so I don't have to worry about it. No, we exercise caution when it comes to electrical safe work practices, and electrical safety is really important that we realize the GFCI, our personal protective equipment, our gloves, our hats, our shoes, our fall protection, all of that is when stuff went wrong. Okay, a GFCI is not your leading level of protection. GFCIs are there for when things go wrong, and hopefully they will do their job, because just like anything else, just because you're on a GFCI circuit does not mean you can't be electrocuted, you can't lose your life on that circuit, because it's all dependent upon your connection point, and we're going to talk about that as well. So you put your hands around hot and neutral, you're a load, and GFCIs are not going to trip. And we're going to understand the technology and why that is the way it is. But in this case, GFCIs are not your first level of defense. So GFCIs require an equipment grounding conductor to operate. 99 said true and 80 said false. If this was true, that would mean I cannot use GFCI on knob and tube wiring. I could not use GFCI on older wires in homes. I do not need an equipment grounding conductor, and we're going to talk about the technology and help you understand why that's the case. But GFCIs will function even if there's just a hot neutral and no equipment grounding conductor going downstream. A GFCI circuit breaker, GFCI receptacles are going to give you their level of protection and trip anytime the current goes out of the normal path, and the equipment grounding conductor is not the normal path. The equipment grounding conductor is there to create that low impedance path for the short circuit currents and things like that, to establish everything at the same voltage potential, but it's not there to get that GFCI to operate. So you can use a GFCI circuit breaker, you can use a GFCI receptacle on your knob and tube wiring and your older wiring where you may not have a neutral, or they may not have a ground. So Blake Reader, I just looked down. Is it true that even with nothing plugged in on a GFCI receptacle outlet, the neutral still has voltage potential on it due to the electronics inside the protection device? Oh, good question. So if you've ever noticed, even when you press the test button and you trip that GFCI receptacle, the little LED lights, where do you think it gets that power from? That power comes from the supply conductors. An AFCI receptacle does the same thing. It's still getting power to that device whenever it trips, because it's going to show you a little indicating light. It is drawing current over that circuit. So good question, and it really helps you understand that there's a brain inside of that device. And we're going to talk about that too. But so the right answer here is false. That was 88. It does not need an equipment grounding conductor to operate properly. You can place two GFCI breakers next to each other and use a handle for two 40-volt circuits. 142 of you said false. Very good. The reason is because it's a 120-volt device, and also the technology inside will prevent you. It will nuisance trip if you share the neutral. And if you put a handle tie on it, it's rated for 120 volts. You will violate the NEC requirements that tell you that you can't have a device that's not rated at the voltage it's being applied. Because the moment you put two single pole breakers with a handle tie, that's right, I should have said that in the question. The moment you put a handle tie across that, then you are operating that not at 120 volts, you're operating it at 240 volts. So thank you, David Engelhart. I should have put two single pole breakers. My quiz, I made it up really quick last night, and that's why you didn't get it early. So you cannot put a GFCI receptacle downstream of a GFCI circuit breaker because they will have nuisance tripping. We got 56, 57 say true, 117 say false. 8 of you are lost. So this question comes up, especially now that we have expansion of arc fault circuit interrupters. AFCIs now have expanded through a lot of areas where there are GFCI requirements. And if I have a place where I have a GFCI or an AFCI circuit breaker upstream, and I have a GFCI receptacle downstream. So I have an AFCI and a GFCI dual function device upstream. I have a ground fault circuit interrupter GFCI downstream. The question always comes, well, can I do that? Is that an error? Is it a mistake? There are no compatibility issues between those devices. Whether it's an AFCI upstream and a GFCI downstream, a GFCI upstream, a GFCI downstream, you went above and beyond. You have 2 levels of protection for the same circuit, and that's fine. One's not going to trip before the other. It's a pot shot. I can't tell you which one's going to open. If you had a fault, if I had a GFCI circuit breaker protecting the entire circuit and all of my connected cords, and I had a GFCI receptacle protecting anything downstream, if I came in contact, or if a metal object came in contact and created a ground fault, I can't tell you that the receptacle is going to trip first and the breaker is not going to trip. They could both open. They could, one or the other could open. The only thing you can rest assured is that that something will open, and you probably paid a little bit more for that circuit than you should have, but that's okay. I've seen some garages where every single receptacle in the garage, it's all the same circuit, every receptacle had a GFCI in it, and that's because whoever did that installation didn't understand that you put one GFCI receptacle in and it protects what you plug in, and it connects anything that's connected downstream. So that's why it's really important to practice social distancing and take a class. So in any case, that's the way it goes. All right, you cannot put a GFCI receptacle downstream of an AFCI circuit breaker. I just answered this one, and most of you agree with that. You can put a GFCI receptacle downstream of an AFCI circuit breaker. You can also do vice versa. You can have a GFCI circuit breaker upstream of an AFCI receptacle. So there's no compatibility issues between those technologies whatsoever. Right. Let's go through another question. You no longer have to test GFCIs because the standard now includes self-test requirements. All right, so this is the new GFCIs on the market. I can't remember what year it was. I don't know if Jeff Fecteau's out there. He probably knows the year. I don't know if it was 2014 or 15 or somewhere in that ballpark. 2015, Mr. Nihad El-Sharif. Thank you very much. In 2015, the standard went into effect that had to have self-testing capabilities because there was a NEMA study that was done that basically a NEMA study looked at took a bunch of GFCIs, whether they be a circuit breaker or a receptacle, from the field, and they analyzed them. They found that there were a lot of failures inside those receptacles. So they changed on the ground fault circuit. They changed the GFCIs. They changed the GFCIs in the system in the standard so that there's self-testing capabilities, and what that does is that'll test a lot of the mechanics, a lot of the electronics inside the brain, make sure the brain is going. There are some things that self-testing doesn't test. For example, if I have an extremely high short circuit pass through that device, I could possibly weld the contacts. If I have an abnormal event in my power distribution system, the contacts could be welded. Testing that button will make sure that those contacts are separated. The self-test feature, if it finds a problem, most manufacturers, I think all manufacturers, the way they implement the requirements in the standard, it will find a problem, and then when you press the test button, the device will trip, but it won't be able to reclose. So it won't just open on its own. You could design it that way, but 9 times out of 10, you probably wouldn't want that to happen. We have a requirement to test on a monthly basis, and I know a lot of industrials out there, they have GFCIs in their plants, and that's one of the biggest questions I always get. Do I have to test monthly? Do you have anything that says I don't have to test monthly? You have to test. OSHA tells us we have to test monthly. The manufacturer's instructions tell you, because the standard wants it in there, to test monthly. But now, here's my advice. Never trust whether or not that device has been tested monthly. In any place, you go to a hotel, in your home, no matter where you're at, push the test button before time of use. That will ensure that it's working and functioning for you. Okay, so that's just a little tip. Number 1 is test before use, but you're supposed to you're supposed to do the press the test button. I'm just going to take a look at monthly from the manufacturers, from OSHA perspective. So Nihad made a comment. If he remembers correctly, anything before, obviously, that when a standard changes, you don't have to. You can't go back to an older product. So anything before July of 2015, and July is the date, didn't need to meet the self-testing requirement. Anything after that fact does. All right, so I didn't want to do what I just did. Let's go back to the quiz. So the right answer on this one is false. And that was the quiz. So now that we got the quiz out of the way, we can move on to our regularly scheduled program. All right, here we go. Are you ready? We know what a GFCI is. It's there to protect, and we call it a Class A device. Now you'll notice in this slide that we have this note down here on the bottom that basically gives us an informational note. Now we know in the National Electrical Code, informational notes are not enforceable. Informational notes are there for what? Information. So what if this informational note's telling you is that whenever you use the term ground fault circuit interrupter in the National Electrical Code, you're talking about a Class A device, and a Class A device trips from 4 to 6 milliamps. So that's an important piece of this puzzle. If you look at and this is a good slide that my good friend Nihad Al Sharif put together, and he did a great job of explaining the differences on what a Class A, Class C, D, and E devices are, and when you get into those. So if your voltage to ground is over 150 volts, if it's not, then if you have an equipment grounding or double insulation, if you don't, then you're in a Class A GFCI. What this shows you is this topic of what do you call double insulating a device is important, because this concept right here, if I take a product and I provide double insulation to it, and provide, that basically helps reduce the likelihood of coming into contact with something energized, then I'm into a Class C type of device, which are different trip levels. It might not be a 4 to 6 milliamp, but this is a nice little slide that gives you a little overview of the different classes of devices and when you might see those. Now let's talk a little bit about how a GFCI works. So this is your line terminals over here on the left-hand side. These are your load terminals, and We're going to walk through the hot and cold, the hot and neutral, or the grounded conductor and the ungrounded conductor. That's the best way to put it. Now you'll see here that you're providing power to the face and you're providing power to that load terminal. So when I daisy chain these, when I run these in series with a circuit in series, that this GFCI will provide protection for anything plugged into the face of that receptacle and anything downstream of it, as long as it's connected in series. And I believe Mr. James Mercier, you made a very good point that it really depends on if those GFCIs are in series or parallel in the garage. So it may be that every one of those GFCI receptacles in that garage were daisy chained on the line side from device to device to device instead of through the load terminal. So good point, James. And there might be a very valid reason to do that. So power goes out to those, and then it comes back over that neutral. And you'll notice everything goes through the donut. Okay? Now I'm getting hungry. Everything goes through this donut. That we call that the ground fault sensor. We'll call that a zero sequence CT for the engineers on the phone. But that's basically a current transformer. And the Gazaltas have to equal the Gazintas. So everything that goes out, all of the current that goes out has to equate to what comes back. That is what establishes your protection. Here's what's inside of a GFCI circuit breaker. There is your CT, okay? And what you're seeing is this is coming in from the load. This metal, or this goes out from the load. This metal is connected to over here, and it comes down through and goes through the donut. This over here on this side, this is my thermal magnetic. So the brain is in here. There's the brain. You have to connect the pigtail. If you don't connect that pigtail, the brain doesn't get power. You just bought a very expensive thermal magnetic circuit breaker. Okay? That pigtail has to be connected. That powers the brain. So this system has to work. Now, you may have a breaker that doesn't have the pigtail and it plugs right onto the neutral. That way you don't have to worry about a pigtail. That makes life a lot more simpler for you. But if you do not plug that pigtail in, the brain doesn't get power. If the brain doesn't get power, you'll still be able to turn on the circuit. You just won't have that protection. But when you press the test button, this is the only way to really test a GFCI or an AFCI, is to press that push to test button that's on the device. That goes for a receptacle as well. Any of those handheld units, those are indicators. You don't want to rely on that to say that the device is working or not working. And for the most part, you'll get a false negative, not a false positive. So if it trips it, it's working. If it doesn't trip it, that doesn't mean the breaker is bad. That means you go down to the breaker or you go to that receptacle, press the button, and confirm it. All right, so this is the circuit breaker. This is how the circuit breaker works, and you'll see, this is the contacts that do the job in breaking the circuit. There's a trip solenoid involved. There's electronics. There's your brain over here. This is your brain. This is your CT. There's a CT in every one of these devices. Current goes out and back and through the pigtail. I like my little pigtail. That took me hours to draw. Hours to draw that one. That's okay. Did it all for you guys. Yeah. So the current goes through the CT and comes back. So if I press the push to test button, so I don't know if you saw that little wiggle up there. I'm going to press this push to test button. I'm going to show you what happens when I do that. When you press the button, the current flows through the button, through a resistor, and you'll notice it goes around the CT. That current doesn't come through the CT, because the key thing to remember about a GFCI is anything that goes out through that donut has to come back through that donut. Any of the difference, if the difference in that current is greater than 0.04, so 4 milliamps to 6 milliamps, that's going to trip that device. And then when you look at these cord appliance things, we pack a lot of stuff into a small space in this type of equipment. But you still have, there's your CT. You're always going to have that current transformer in there. There's your electrical, mechanical disconnects and all that good stuff. Now, these devices have to go through a little bit different types of testing, but they work on the same principle. There's sort of the diagram. There's an electromechanical latching device. Here's your circuitry with open and grounded neutral detection. We might touch on that a little bit. And there's your push to test button. So, all of these should be tested. I would say always test the GFCI before use, regardless if you're testing it on once a month. You should always test a GFCI before you use it. You've got to plug into something. If you have this product in your hand, you're carrying it out to a job site, plug it in, turn it on, test it, and reset it. It takes a couple seconds. It's not very difficult. So please test before use. Now this is just a little example. You have there's your donut, right? So if I'm supplying 5 amps to this load, and how you like the water, I think Lance and Raleigh did this slide. I copied this off him a long time ago. And if I'm sending 5 amps out and only 4.993 comes back, that means I have 7 milliamps of leakage current. That GFCI is going to open. So that's basically the function of how it works. And it doesn't matter if it's going through you, it doesn't know. Electrons are dumb. I mean, they're party animals. They love to go to the fault, but they're not the smartest things in the drawer. They will go anywhere. They don't care about what building they're in, what structure they're in. They don't care if they're going through you or what they're going through. As long as they find a different path away from that neutral, they're going to take it. And this is going to detect it and find the issue. So this is an example. I get this question a lot from a different, from like an appliance perspective, and sometimes you may not even have that neutral. I know some spa panels and pumps, they run 2 hots out there, and that's all they got. And then I'll get the question, will it still work? And yes, it will still work if current goes outside of the normal path, and it is greater than 4 to 6 milliamps. That device is going to open. I don't need a neutral going to the load. If it's if it's just a hot neutral, you're going to need that to complete the circuit. But if I have 2 hots going out to a pump motor or something like that, I'm still going to detect that. Now, to prove how much he knows about electricity, Joe is going to walk out. He's got a generator that's isolated because he says, there's no ground fault return path because I've got this generator. It's a separately derived source. I'm not bonded. I'm not grounded. So I can go out there and touch these conductors because I'm a bird on the wire. And he grabs hot and neutral. What happens to Joe if he grabs hot and neutral? Joe becomes a load. And a GFCI will not trip. I don't care if he is grounded. It is grounded from a separately derived system, and it's grounded or not grounded. If you grab hot and neutral, you are part of the circuit. You are now a resistor, possibly a little bit of inductance. If you were in our class yesterday, you'd understand resistance and inductance, but you've become a load. And I know I've been called a load, but you're becoming a load on the circuit, and you're toast. The GFCI is not going to help you. Arlene Donaire, I don't have your email, so I can't really send. Somebody can send Arlene Donaire a link on WebEx. I don't have that. I have your email account. All right, so ground fault protection of equipment. A system is in the way, if you look at, we have to understand the difference between GFCIs and GFPE. GFPE is equipment level protection. And if you look at the definition in the National Electrical Code of GFPE, it says the protection is provided at current levels less than those required to protect conductors from damage. So if I have a conductor that is 20 amps worth of conductor and I'm protecting it at 20 amps, I know my GFPE is going to trip less than that. If my GFPE could be that 4,000 amp circuit breaker up my main, and I have it set to 1,000 amps or 1,200 amps. That's ground fault protection of equipment, but it's less than the rating of that equipment, and it will hopefully detect a fault inside that equipment or downstream. The GFCI is the 4 to 6 milliamp, and we already talked about the 4 to 6 milliamp, and that's a basic fundamental that GFPE is not there to protect you and me. GFPE is to protect equipment. 943, a UL 1053 is equipment protection. A UL 943 is people protection. Trip times faster than around 15 milliseconds on GFCI. 1053 is a lot different. So let's talk about some of the trip characteristics on a 943 device. This is a curve that shows the heart fibrillation thresholds, and we're going to talk about that because that's a fun discussion. We're going to talk about the heart fibrillation thresholds for a normal healthy adult. That is important. A normal healthy, people think, oh, GFCIs will protect everybody. Okay, it's a normal healthy person, adult. So that level of threshold that's an important thing. If you have heart conditions, you have other medical conditions, it doesn't mean your GFCI is going to protect you. I have this discussion. I do electrical safe work practices training, and Jim Dahl at Local 98 pointed this out during a class one time. And I never really thought about it this way. And he asked the question, he says, if you're wearing fall protection and you fall off a scaffolding, is that going to save your life? Are you sure not to be injured, have a fatal injury? And the answer to that is no, you're not assured of that. It's going to prevent that abrupt stop at the bottom, but you don't know what might happen to you. Even though you're wearing your fall protection, even though you have that GFCI, there may be other circumstances that could still lead to shock. You'll reduce it significantly, the incident of it, but it doesn't mean it's a sure thing. That UL curve, there's an equation for this UL curve. And then in reality, GFCIs trip a lot faster. It's not because that's the design and that's what our goal was. It's just because of the sheer physics and the way GFCI it opens. It just acts that fast. So you get a very fast response time. There's the equation that I was talking about. Thank you, Nihad El Sharif, for the I think we got that. That was out of UL 943 equation. You have your Class A device, 4 to 6 milliamps, and then you have your Class C and D devices up there at 20 milliamps. That's their pickup threshold, but you can see your GFCI protection zone. UL 943 is the standard, and these are we have performance, withstand, environmental. So we have a lot of performance requirements. I'll say that if you have a UL 943 circuit breaker, it's tested to UL 943, obviously, in all of these types of performance, withstand, and environmental testing. We also will test it to UL 943. And if it's an arc fault, ground fault device, it also gets tested to UL 1699. So if you had an AF-GF dual function AFCI device circuit breaker, it is the most tested breaker, in my opinion, on the market because it goes through UL 943, UL 489, and UL 1699, and if there's probably another UL standard in there, I don't know if UL 2000 or whatever that number is for the brain is also in there as well because it has a microprocessor. So, that device is a UL 943 device and it responds very fast. A GF ground fault protection of equipment. This is what's in the UL standard for ground fault protection of equipment at 85% of the pickup, which I define as the manufacturer, right? So I tell you, this is a 100 milliamp device, or this is a 30 milliamp device. 85% of the pickup shall not trip. 115% of that pickup, so 115% of 30 milliamps, ultimately it has to trip. Ultimately, I don't know what ultimately is. I don't know if you run the test, you go and say, hey, let's go out grab a sandwich at Permani Brothers and come back and see if this thing's tripped. I don't know what that means, but it's ultimately it has to trip. At 150%, you got 2 seconds. At 250%, you have 1 second. So not quite a GFCI response capability for that device. So let's I want to just real quickly walk through this topic of ground fault protection of equipment because I think it's a good discussion to understand some of the history there. GFPE entered in the National Electrical Code in 1971, and that was a service entrance equipment. And to understand it's interesting to understand why it went into the code and what its function is. They were having problems in the 60s, 50s, 60s, and into the 70s, and with arc flash events and burn downs of service entrance equipment. There were 3 changes in our history, in our electrical history that occurred that caused the need for GFPE. One is we went and we said, we don't like these ungrounded systems. Why? Because ungrounded systems, voltage fluctuations, I'm burning up motors, I have all these issues in my power distribution system because I'm ungrounded. And so they said, let's ground it. Opportunity number one for GFPE. The second thing they did was they said, we're going to increase the voltage from 208 to 480. You know, I can distribute my voltage better. I can run 480 volt equipment instead of 208 volt equipment. These new products came on the market. They seem to do some great job for this manufacturing facility, etc. So now we increased the voltage. And the third thing that we did was we went from a service of an average of 600 amps to 4,000 amps. So think about it. And if you were in the class on Monday and Tuesday, Monday we went over short circuit currents. Tuesday we went over selective coordination. And we know, because of our selective coordination discussion and the trip curve, the resume of a circuit breaker or a fuse, if you take a 600 amp device and increase it to 4,000 amps, the instantaneous just went way over to the right. I guess that's your right. I don't know which one's your right. The instantaneous is much higher. The fact that I raised the voltage means I'm pushing more current. And I've raised the voltage, but I've lowered the current. So now I have lower fault currents, lower currents that are in the long time region of these devices. And that's why you needed GFPE. Incident energy events started to occur because I had a delay in the ground fault in the protection of those larger breakers at the service entrance equipment. We had examples of burn downs on service entrance equipment. If you look back at the public inputs and public comments for the 1971 code, you'll see all of those arc flash events. There are some good papers, IEEE papers, that are written around this topic. And that's how ground fault protection of equipment came to be. And at that time, think about it, it's late 60s, in the mid 60s, Westinghouse was working on taking a microprocessor and putting it in a trip unit. So we had new trip units that were on the market at that time. And in that brain, we gave it the capability to detect ground fault. And that's how ground fault protection of equipment evolved into the NEC. So it was into the late 60s. We had a new product on the market. It seems that would address the issue. And then it became a requirement in the National Electrical Code. And then as time moved on, electronics got to be smaller and smaller and smaller, and then we were able to put it into smaller breakers and even receptacles, and now you have ground fault protection capabilities in those smaller devices. So that's just a little quick background on GFPE. So let's talk about the hazard, because it's important. If I want to understand GFCIs, which we talked about GFCIs, we talked about how they function and operate, but now I sort of want to talk about the hazard a little bit and why we have GFCI protection. NFPA 70E is the Electrical Safe Work Practices Reference. If you're not a member of NFPA 70 or NFPA, you should be. If you're not aware of NFPA 70E, you need to be. And that document helps us understand, and I love Annex K of that document because it's a good read. You know, not too many people read the annex material. You know, we're so focused. There's a couple of things we always do. We throw away instructions. That's usually Article 90, and then we don't read the annex materials. The annex material in this case is a good read and helps us understand. Electrical injuries represent a serious workplace hazard. It's not just for the electrical worker, it's also for the non-electrical worker. So what they've learned is the electrical incident of electrical injury. If I'm on a job site, my plumber could die from electricity. The carpenter could die from electricity. The homeowner who has nothing to do with our electrical industry could die from electricity. So we have GFCI protection, not just for us who work in the industry, but for anybody who is interfacing with electricity or using appliances and tools and all these great things. So again, in Annex K.1, they'll tell you that a large share of non-electrical workers, about 1/2 of the incidents involving workers outside of the electrical crafts, and that's just the crafts. That's not those who are where the shock is coming from in the residential areas as well. Now, what we know about electrocutions Over 600 people die from electrocution each year. Over 30,000 non-fatal electrical shocks. Now, it can be non-fatal, but remember, when current passes through the body, it'll find those low impedance paths. Unfortunately, that's through our veins and through those very high saline salty solutions where it passes through your veins. And then where do your veins go? To your organs. So you may have a non-fatal, but it can still cause injury that could be permanent or long-term at least. So it's the fourth highest cause of industrial fatalities. Now, this is an older curve, but I find this one fascinating personally. If you look at the causes of electrocutions, it's the fifth leading cause of death from 1980 to 1995. I know it's dated, but and I could probably update this, but it's phenomenal to me that homicides on the job site are one of those. Machine-related deaths, yep. Motor vehicles, get it. Falls, absolutely. Homicides is above falls. But electrocutions is that fifth one. And what I love about this curve is it's showing you a downward trend. And if I think about I hope Larry Ayer's on the phone. If we think about our journey in safety, no matter where we're at, unfortunately, safety is something that we rely on codes and standards to drive because it adds cost and it's something you don't see. Hopefully you don't even know it's there. Like, I don't know there's an airbag in my car. I'm not looking at my airbag saying, what color is it? I'm not talking to my wife about, hey, do you want a leather airbag or do you want a silky airbag? What kind of airbag do you want? Do you want a white one, a green one? You don't see it unless it deploys, and hopefully you never see it deploy. But it's a requirement. Wearing your buckles are a requirement, right? So requirements will unfortunately drive safety. And in our power distribution systems, we rely on things like the National Electrical Code and UL standards to increase and address the safety concerns in this power distribution system, as well as our knowledge. So from a product perspective, as a manufacturer, I want to list my products to third-party listing agencies because I want everybody who makes a GFCI to test this. Arlene Donaire, I sent you that email. You should see that in your inbox. So in any case, the GFCI functionality and any of these products probably should be UL listed solutions. And if they are UL listed solutions, that means everybody's going through the same level of analysis and it's getting third-party review, which it helps increase the likelihood that it's going to be a good product doing what it's supposed to be doing. These are some of the safety standards and enforcement, and you have the construction codes from NFPA and ICC and all that good stuff. All right. So it is the intent of, so now the examination, that's another important 90.7 is examination of equipment for safety. So this references Annex. So this is going to tell us that inspectors are going to be looking for the listing of some of these products where it's required by listing, but any inspector is going to be looking at a product and they're going to make sure that it's doing what it's supposed to be doing, and they're going to leverage language like you find in 90.7 and an informative annexes for references to the GFCI standards for the products that they're looking at. And again, applicable product standards recognized as achieving equivalent and effective safety for equipment installed to comply with that code. Now, I show this trend, and this is a downward trend of shock. The numbers of deaths are going down. It's not just because of GFCIs. We have double insulated tools. We have all of these other different things that are happening in our world that help prevent shock. So we're much more knowledgeable. There's things that aren't being done that have been done in the past, and that saves lives too. But the good thing is all of this is sending the trend down. Now let's talk about the hazard of shock. The magnitude of current that flows through the body or through your body is important. The path that current takes through the body is important. If it goes through the heart, much more critical than anywhere else. And the amount of time that I let that current flow through the body is all a part of shock. Now, the magnitude. The amount of current that flows through the body is dependent upon the circuit. We talked about this on Monday with short circuit currents. We talked about the impedance and Ohm's law and all that good stuff. It's important that we understand the magnitude of current that flows through your body is dependent upon your resistance, the resistance of the circuit. And we have a lot of information to help us understand that value and what the amount of currents do to the body. The fact that we know 0.5 to 3 milliamps will give you a tingling sensation. 3 to 10 milliamps is when muscle contractions and pain start. And 10 to 40 milliamps is when the let go threshold is. And we talked about that in one of our questions. Now, I always look at this, you look at charts like this and you wonder how much beer money was earned off of getting this data, right? And unfortunately, I usually joke about stuff like that and say, yeah, I can just see some college student or some employee somewhere saying, hey, let me put this current through you. Unfortunately, that's how some of this data came about. In my research, I found the earliest documentation available that I'm aware of was research that was done around the electric fence. And the story there is really interesting. But that's a study that was done where they came up with some of those data points from the resistance of the body. The magnitude of current depends on the impedance of the circuit, which could include a person. Now, we know that from a resistance of the body perspective, if our skin is dry, and everybody's going to be different, some people have more calluses on their hand, some people's skin it may be thinner, all these great things. We understand that when our body gets wet and you add water to most things, you're going to reduce the impedance, the resistance. That's going to cause more current to flow. So from a shock perspective, presence, and that's why you see GFCI protection in and around areas where there is dampness, not necessarily just sink areas, food prep areas, etc. The reason we know that is because of the testing that's been done, and all of those people, thank God we have them. We never be able to do some of this testing today. This was that electric shock as it pertains to the electric fence back in 1939. So we're talking 1930s when a lot of this testing was done, because farmers were putting wire around areas of their farm, and they were unfortunately killing kids. So if you look in the 60s, Dalziel came out with some testing, and he published the dangerous effects of electric shock in October of 1961. And here, the picture that we're showing on the screen is a guy who's testing. My tongue is I can even taste the battery on my mouth. He's detecting the sense of voltage and current on his tongue. In the IEEE Spectrum magazine in 1972, Charles Dalziel published some more of his research, and what you're seeing there is an individual where they put a terminal around his bicep, and they put a metal bar in his hand, and they were testing the let go threshold to determine those let go thresholds. And so we have a lot of information that helps us understand when body comes through the current, what is imperceptible, when will there be no permanent harm, but you have perception of that current. And you'll notice that we have our 4 to 6 milliamps. There's 5 milliamps is what they determined. Now we trip anywhere from 4 to 6 milliamps, but 5 milliamps is what, if you follow that line B down, that's your Class A device. That's your threshold. It's going to make sure that you trip fast enough that you don't have this red area over here is what we call the let go threshold, right? This is your involuntary muscle contractions. You can't let go of something. And you'll notice that you have a pickup point and then This is the duration up the side. So this is just like a TCC curve. In any case, you have your current across the bottom and your time up the side. So that gives you a sort of an understanding of ventricular defibrillation. And your European standards are into the 30 milliamps because they're going to permit they're not going to claim that you won't have let go issues, right? They're not into the defib issues from C1 and up, but they are into the area of involuntary muscular contraction. So from a European standard perspective, they permit 30 milliamps and they call it people protection. But in the States and the US, they don't do that. That's basically the difference is that the European model is to, oh, and it reconnected. All right, so I'm still online. That's a good thing. So the path that goes through the body is important. If you are, for example, if it's going through the heart or if it's going through your arms, side of your body, the chest cavity is the area of most concern for obvious reasons. So I see a question on YouTube. If you have a single outlet circuit like a fridge, can I use only a GFCI outlet, or do I need to protect the entire circuit with a GFCI? You can use a GFCI receptacle, but it has to be readily accessible. Or you can put it on a GFCI circuit breaker, one or the other. If you use it, you can also, there's a blank face GFCI that you can put that is in a readily accessible area that will provide GFCI protection for that load. This is sort of the reason why we have GFCI, because the circuit breaker infuses aren't going to trip at those lower thresholds that cause damage to your body. So we know that the magnitude of current, the path the current takes to the body, and the time are all critical factors regarding regarding shock. All right, so I'm going to go into 210.8, but I'm first going to look at some of the chat stuff here. Let's see what we got. Standard, yes. There's also an ASHI report. If I remember correctly, 943 stated that. Okay, we already talked about that. What's the worst that can happen if the device fails to trip? Ooh, if it fails to trip, you could die from electrocution. That would be probably the worst. Some contractors require testing before you choose. That is a good thing. That's a principle. 5 amps to a table lamp. Yeah, that's a big. Thanks, Dawn. That's a big table lamp. You have no idea the lighting that I have in my basement. I was not picking on Joe Fellow. He's a good man. If they are tripping at the maximum permitted time, you would have to hold the test button for about 5 seconds. Don Ganir said. Please explain the leakage. Leakage, I will talk about leakage. So here's the concern whenever you get into a GFCI discussion. Some of the products that provide, some products may have inherent leakage current, or from an operator, you may have leakage current at higher frequencies as well, where you have magnetic coupling and things of that nature. So the GFCIs will detect, anything that goes outside of the path. So if I have GFCIs and I have that are feeding, say, GFCIs in my say in my branch or my feeder circuit higher up in the system, I could have multiple appliances plugged in that will cause leakage current. Now here's the key thing about leakage current. Always check. A lot of people say, well, I have all these appliances in my kitchen, and all of those are going to add up and trip my GFCI protection if I put it in the circuit breaker. The reality of it is most of your appliances only have 2 prongs. That's because they're double insulated and they have other provisions in place, but you can't have leakage current if you're only using a hot and neutral. The moment you have the equipment grounding conductor, now I can have leakage current over that equipment grounding conductor. So anything that has a 3-prong, I could have leakage current. And the addition of leakage current, if you have a lot of different products installed, I know this became a concern in Article 555 for marinas, because there's new GFCI and GFPE requirements in marinas, and every boat will probably have some leakage current. There was a concern about that, but it could add up and You could have a trip just because of leakage current and everything is working fine. UL standards on appliances, I believe it's UL 101 if I'm not mistaken, do have requirements that appliances aren't to have a leakage currents above a certain value, so that helps reduce the leakage. But suffice it to say, for the most part, like my house, every circuit in my house has GFCI protection, and I put it there because yes, UL 101 is the thanks Jeff Victo. So the UL 101 is the appliance standard. So I have GFCI protection on every circuit in my house. And I did that because I had water damage. I had 45,000 gallons of water come down through this house, and not all of my lighting was replaced. And I wanted that reassurance that all that current went out the hot and it all came back on the neutral. And I don't have any nuisance stripping issues. I have a 1950 something refrigerator. I've got a 1959 Wurlitzer jukebox. No issues with any of those solutions. So leakage current could have. It could be higher frequency leakage currents. It could be that there's something inside of that appliance that just is using that equipment grounding conductor for whatever reason. That's putting current over the equipment grounding conductor. But that was a good question. Does having multiple GFCI outlets in an exterior circuit create enough leakage current to create a nuisance strip condition? No, it doesn't. You could have GFCI outlets. GFCIs do not create leakage issues. The GFCI circuit breaker or GFCI receptacles are going to make sure that all that current is on the hot and neutral. So that's an important aspect. With a European model at 30 milliamps at a maximum of 30 milliseconds, would we still see muscle contraction? 30 milliseconds, probably not. If you looked at that slide, the amount of time that you had the flow, you probably would not have muscle contraction. But now remember, that's at 30 milliamps. Higher currents, even at 30 milliseconds, you could have muscle contraction. It depends on how much current's flowing through the body. And remember that the GFCI or GFPE does not limit the amount of current that passes through your body. If you're connected to a circuit and you're going to draw 5 amps, you're drawing 5 amps. The GFCI is going to trip and make sure it trips, so your heart doesn't go into defib, but you're still going to see 5 amps. NERDLs, not just UL. Yes, so there are nationally recognized testing laboratories, and UL, so when I say UL, I'm talking the standard. So when I say UL 943, that's an underwriter's laboratory standard. Anybody can list to that standard, and any nationally recognized testing laboratory can list to that standard, but it is a UL standard. Okay, let's look at the YouTube. The airbag story was great. Excellent, thanks, Bill. Be a choice to have airbags. GFCIs and AFCIs are not mandatory. That's true. And the code adoption is an important part of that pie. And thanks, Ryan. Yeah, 6479. Great document. Interesting to see their information. Okay, let's move on to 210.8. All right. Moving. How do I do this? I have to hide some things. Hold on. Give me a break. Having a technical. My chat box is hiding something I need. Take that off, and here we go. Whoops. I don't want to do 555. If we have time, we'll do 555. We're going to go to 210.8. Here we go. So I hear somebody's muffling around. Their microphone's not muted. Please mute. Okay, 210.8 GFCIs. Are you ready? 210.8. This is how 210.8 is laid out. You have A through F. Dwelling units, other than dwelling units. Boat hoists, that's now out of the code. I mean, it's moved, not out, but it's moved. Crawl space lighting outlets, specific appliances, equipment requiring service, anything that's underlined and got that little star, that is a 2020 code change. Important thing to remember. Now, in dwelling units, one of the things we did in NEC, in the 2020 version, NEC, we expanded the dwelling unit requirements to all circuits, all all circuits, receptacle outlets, and this is the importance, all receptacle outlets in the areas that are identified in 210.8a. So that's another important thing to remember. We have various areas in 210.8a, and we have GFCI requirements, and we've expanded to say any receptacle outlet in any of those areas, regardless of the amp rating of the circuit, needs to be GFCI protected. I'll talk about that a little bit more. Unfortunately, in the GFCI world, substantiation for code changes is built around death. Minor modifications in other than dwelling units, then basically what you're seeing in 210.8 is an alignment between A and B. So we have people out there who use the code, will make a change, and they'll say, hold on, you're telling me that this is a hazard in a dwelling unit. I got this crawl space over here in a dwelling unit, and that electron knows that that crawl space is over in a commercial building, and it's not going to be a hazard over there. That just don't make sense. So we did some things in 210.8b, and we did some things in 210.8a, where if we have a hazard in a dwelling unit, and there's the same situation in other than a dwelling unit, we need to make sure they're aligned with each other. So we did some of that in this cycle. We did some of that last cycle, and I'm noticing we're probably going to do that in the 2023 cycle. Boat hoists. We deleted boat hoists because that is already in Article 555. We did a lot of changes in Article 555. If you do marinas or you have a marina, you're doing work in and around a marina, you got to check out Article 555. Now, in D, specific appliances, we changed the language to align with what was changed in 422. We've got a little struggle going on between Article 422 and Article 210 in Section 210.8. They're sort of stepping on each other's toes a little bit. We need to clean that up. I think in the next cycle, we tried to do some of the cleaning up this time, but the journey of appliances and GFCI protection is continuing, and we're trying to clean things up. So we added a section in 210.8 D, specific appliances, to try to help clean it up. In my opinion, it's still not done. So you're probably going to see some work in there in the 2023 cycle. And just for clarity's sake, I do sit on Code Making Panel 2, but I am not speaking on behalf of Code Making Panel 2. I am not speaking on behalf of NFPA or anybody else. These are my opinions and my opinions only. I got to add that to the intro. Equipment requiring servicing. This is 210.8E. What we did here was we made some changes back in 210.63 as well, with regard to where you're required to have a receptacle outlet for the maintenance person. They need to plug tools in, and they need to make sure that if they shut the equipment off, that receptacle is still powered up. So we made some changes to help make that clear, but now we have a requirement that those receptacles have to be GFCI protected, because there are cases where that equipment may not be in an area that already requires GFCI protection. And then we have the outdoor outlets. We expanded to outlets. Now this is why I had that question in there. It's not a receptacle outlet, it's the outlets, and we're going to talk about that as we get through there. Now, over the last two cycles, GFCIs have expanded, I would say, considerably. And unfortunately, it was the examples of electrocutions that has driven those changes. I know it presents a challenge in code adoption, and we have a lot of questions around that, but nobody should be dying from shock in their residential home or in areas, because we have the technologies. They're not that expensive. The hazard doesn't change just because the circuit is greater than 20 amps. I could have a 20 amp receptacle outside, and I have to GFCI protect it, and there could be a 30 amp receptacle outlet feeding some piece of equipment, and I don't have to GFCI protect it. And some public input, somebody somewhere scratched their head and said, what's up with that? And the code panel said, we agree. And unfortunately, we had a death. So we had a few deaths, which we'll talk about. Just doesn't change. We already talked about GFCI protection. So let's talk about dwelling units first. Here's what we did in dwelling units. You can tell the language that we did. We crossed out the single phase 15 and 20 amps, and we just said through 250 volts. So that basically says all 125 volt through 250 volt receptacles installed in the location specified in A1 through 11 and supplied by single phase branch circuits rated 150 volts or less to ground shall have ground fault circuit. So the key there is receptacle outlets. So any receptacle outlet in those areas needs to have GFCI protection. I'm not going to go through what the definition of a receptacle is. Maybe if we have time at the end, I'll do that, but I don't think I'll have time. So we removed that language, expanded GFCI protection to any receptacle outlet. I already said that. And that cleans up some language to make, we always have to worry about the details. Unfortunately, here's what happens when you do GFCI requirements. As soon as you have a GFCI requirement in an area of the room, say the laundry room, all of a sudden, nobody knows what a laundry room is. We have a crawl space that has GFCI requirements. I don't know what a crawl space is. That's not a crawl space. Basements. All of my basements. I don't know what a basement is. What's the definition of a basement? So unfortunately, we have to make sure the language is very clear. This was one example of why we expanded. 10-year-old girl was looking for some baby kittens behind the family's dryer when she was electrocuted. It's a real story. And a real reason why when you sit on the code panel and you get cases like this, or you get cases like this child in Oklahoma, these are the reasons why we increase safety and we increase the requirements around ground fault circuit interrupters. We lost a 10-year-old Houston, Texas boy. While playing a game of hide and seek, decided to go into the dryer and he was electrocuted. Those are the hardcore truths on why we have GFCI requirements and why we have the expansion and why we see this. If you're working on substantiation, these are the substantiation things that code panels need that really drive the need home. Now let's, if you look, you'll see we made a change in 11 indoor damp and wet locations. NEC 2020. We sort of messed up that language a little bit. It should say damp or wet locations, not damp and wet locations. I have already made a public input for the 2023 cycle to fix that. But if anybody else wants to pile on, send the message. We should have done our homework and fixed that in the code panel, but that's the way it goes. Hello, Mr. Abbasi is on the phone too, and I know Nihad El Sharif is on there. We're both all panel 2 members, so we gotta own up to our mistakes, buddy. Bathrooms. Let's think about bathrooms. We changed, very minor change. We reversed. We argued about this one for at least 20 minutes. Basin and sink. We changed it to sink and basin. No big change there. Garages. We didn't make a change there, but again, garages and accessory buildings have to have a floor at or above grade level, not intended as habitable rooms. If you bring power out to those, you're going to need to have GFCI protection in those receptacles. You have to understand what a garage is, because the moment we have a GFCI requirement, we will have people say, "I don't know what a garage is." All of a sudden, that's not a garage. That's a lean-to. So we defined what a garage is to help you understand when to apply that requirement. Outdoors, we have the only exception on the outdoors or receptacles are those that are not readily accessible or supplied by a branch circuit dedicated to electric snow melting. On the snow melting and de-icing, for those in those areas where they would use that's where you use your GFPE. Crawl spaces, we added that 1990. The crawl space was added in 210.8, and then the substantiation there was, again, the hazard is great, and they also had cases of people that they had 16 fatalities due to faults in portable cords, etc., in those areas. We removed the word unfinished in basements in 210.8a. So now it doesn't matter if it's finished or unfinished. And quite frankly, the issue there was, I don't, my definition of unfinished or finished might be totally different than yours. I may like the rough look where I have the exposed joists and exposed wiring. I think that's great. I threw a carpet on the floor, put a TV on the wall, and that's finished for me. It might not be finished for others. So we took the argument off the table. GFCIs for dwelling units was expanded to all basements. Again, it was always unfinished basements. And then if you have a basement, then the next question is, what's a basement? I've already had that discussion. What a basement is. Go to the building code. So here's the thing. Whenever you have a term that's used in the National Electrical Code, if it is a term that is not defined in the National Electrical Code, then you would fall back to possibly either the building code or Merriam-Webster. The Webster Dictionary is referenced in the protocols for the National Electrical Code. All right, so there's in 210.885 we basically said basements. Kitchens, we did some things. You know, we have GFCI requirements in kitchens. You have to understand what a kitchen is to fully understand some of the changes we did, and actually in 210.8b. That receptacle right there, I've had electrical inspectors, not home inspectors. I was selling a house here in Weirton, West Virginia one time when my wife and I moved, and he tagged me because I didn't have GFCI receptacles in the kitchen. Well, I got a GFCI breaker downstream, and he says, nope, you're violating code. I said, nope, I'm not violating the National Electrical Code. I'm allowed to have a standard receptacle, but as long as I protect it by a GFCI circuit breaker, something upstream, or another GFCI receptacle upstream, I'm good. All of that was protected. Sinks, we got requirements around sinks, and sinks have changed. We changed how you measure so that we can accommodate new sinks that are on the market today. Located in areas, we hit all sinks in 2011 or in 2014. In 2017 is when we changed the measurements from sinks, because, you know, you have these sinks that are bowls that are above the counter, and how do I measure from that? And everybody's fighting over inches because they got that receptacle that they just do not want to put a GFCI device on. Sinks are changing. I got this. There's a picture of a sink that's above the bowl. What do I measure from? How about this sink? Do I measure from below, or the inside the rim, outside the rim? There, and then I worry about the listing of all this stuff, right? Boathouses. Boathouses was added in 1987 in 210.8, and they talked about the fact that you're out there working and you're in and around water. There's an increased hazard. That was the reason they put it in there, and it remains in there. 210.8 in the 14 cycle, we added to address bathtubs or shower stalls. So we're walking through some of the history here, and it's really important to understand where we came from and how we got there. Again, here's an Article 100 bathroom. We changed that definition, put sink in front of basin. We added 10 to address receptacles in laundry areas. And I'll tell you what, the code, a manufacturer came to code making panel 2, and they opened the kimono, so to speak, and said, look, guys, we are having issues when these appliances, we tote these things from house to house to house. That's my washer and dryer. And we've toted those things from house to house to house. And, you know, that washer machine's a metal, and it has water in it, and it shakes all day. And every time we're washing clothes, and it's vibrating. And if I have a fault inside there, I need protection. And I'd still like to find my electrician who did that little cord up there, you know. I don't know if you're looking at that, but that's still a condition I have to fix. But in any case, you know, those are protected because when they fail in an unsafe mode, if they fail. So prior to that 2017, we didn't have a definition for laundry, but because we had a laundry requirement for GFCIs, we had to create a definition, and it's an area containing or designed to contain a laundry tray, cloths, clothes washer, and clothes dryer. And I know there's debate right now on what's a laundry tray. Is that an old term? I don't know. We'll wait for 2023 to figure that out. General overview, expanded to all damp and wet locations. It should be damp or wet locations. Again, we're looking at dog washing stations. The examples, you know, again, we recognize that there are hazards in 210.8b6. You know, we have that requirement in 210.8b6, but we needed it in 210.8a. So it aligned with that. Okay, location, damp. This is what you have to understand what a damp location is. Look at the the definitions. You have to understand what a dry location is and what a wet location is. I'm not here to help you understand that. All I know is we got to protect those pooches. They deserve it just like everybody else deserves it. And these areas may not be in an area that's currently requiring GFCI protection. Now let's talk about other than dwelling units. Another important area to consider. So other than, from a historical perspective, 210.8b didn't exist before the 1993 version of the NEC. What we did before 1993 was we put requirements in chapters 5, 6, and 7 for GFCI protection. That's why back in the marinas in 555, we have GFCI protection. Back in the agricultural buildings, we have GFCI protection. So back in chapters 5, 6, and 7, we have GFCI protection requirements. And then in 93, when they added the language, everything was Kovacevic until this past cycle, 2017 cycle actually, because what we did in the 2017 cycle was we changed it from 15 and 20 amp circuits, and we said all single phase up to 50 amps, or all three phase up to 100 amps or less. Now, what that did was it drove a correlating issue between 210.8b and what was in 5, 6, and 7 back in the back chapters, because they've always been in sync. It was 15 and 20 amp receptacles. Now, all of a sudden, I'm going above 15 and 20 amp receptacles. That created a collision. And in the 2020 cycle, we tried to fix that. There was a task group that was associated. Mike Johnston pulled together a task group for the correlating committee, and they tried to address all of the correlating issues between 210.8b and all of those back-end chapters to get those in sync. But the key here is if you're in other than a dwelling unit and you have a receptacle outlet in any of those locations that are listed, you're not just at 15 and 20 amps, you're single phase up to 50 and you're three phase up to 100 amps. Okay, and what drove that three phase was there was a product that we were looking at from a three phase perspective, which was a solution that wasn't GFCI protection. It was called a special purpose GFCI, and there was good substantiation around that to have GFCI protection in these areas. But we didn't accept that definition and inclusion of that solution because it had some concern around that. But we did recognize the hazard beyond single phase. So here's sort of the journey in 210.8b or 210.8 locations. We had bathrooms, we had rooftops. In 2002, we went to kitchens. 2005, we went to outdoors in public areas. We went to sinks. So this is sort of the journey of GFCIs in 210.8b. We had an exception to rooftops, clarified the vehicle exhibition halls. We had crawl spaces and unfinished basements in the 17 code. And then we continue that journey. In the 2020 code, we made some changes around kitchens, damp, and there's that damp and wet locations. Got to fix that too. Garages, laundry areas, and bathtubs. So this is other than a dwelling unit. So let's take a look at kitchens. We expanded this one. This was I think a significant change. You have to understand that what we said here is kitchens or areas with a sink and permanent provisions for either food preparation or cooking. And if you look at the definition, I looked at this, I had to scratch my head a couple times, and I remember working on the language, but I was doing a presentation at an event, an electrical inspectors event, and I'm like looking at that definition and saying that looks awfully close to the Article 100, because the definition of a kitchen is an area with a sink and permanent provisions for food preparation and cooking. And I look back at this and I'm like, kitchens or areas with a sink and permanent provisions for either food preparation or cooking. I'm like, well, that looks like the same. Looks like I'm saying kitchens or kitchens, right? But here's the difference. There's a big difference. So what constitutes a kitchen? Kitchen needs to have sink and permanent provisions for cooking. That's what the definition of a kitchen says. This is an example of a sink and permanent provisions of cooking. This was one of the hotel rooms I was in. I have a sink and permanent provisions for cooking. Okay, here's a work area that you may have in any one of our industrial facilities or commercial facilities where you have a little break room, right? The break room has a sink, but there's no permanent provisions for cooking. Well, let's take a look at the change, right? So it doesn't meet the definition of a kitchen. So that area that has a sink but no permanent provisions for cooking doesn't meet the definition of a sink. It's what? It's a break room. Well, what we did in 210.8b2 was we said areas with a sink and permanent provisions for either food preparation or cooking. So that work area, this little break room, has a sink and it has a preparation area for food, or a food prep area and cooking. So the other areas, I mean, that this will hit the industrials and all of our facilities where we would, I mean, I think personally that most of these will probably already have GFCI protection just because we have a good habit. But you may have a break room that doesn't have GFCI receptacles in that room. We picked up break rooms. We picked up those areas where, like your Starbucks and your Dunkin' Donuts and other examples like that, where you have receptacles and there's a lot of food prep area. There's no sink. You may think, well, I don't need GFCI protection here, but in fact, you do. At least in the 2020 cycle, you do. Rooftops was added in 14. They added an exception in 14, noting the receptacles on rooftops are not required to be readily accessible other than from the rooftop. We changed the measurements in the 17 for sinks. And then in the 2020 cycle, again, there's an opportunity for change. We got damp or wet locations. That's in 210.8b now. So we have it in A and we got it in B. Garages, this is another significant. We added accessory buildings in 210.8b. That's a significant change, I think. Garages, accessory buildings, service bays, and similar areas other than vehicle exhibition halls and showrooms. And that's, I think, significant in 210.8b. So if you have accessory buildings in a other than dwelling unit, you got to think about those. We added laundry areas in other than dwelling units. So if you have a laundry area, that whole area is going to have to be GFCI protected. And again, remember, we have a single phase and a three phase. We're going above, beyond 15 and 20 amp receptacle outlets. So keep that in mind. Bathtubs and shower stalls, where receptacles are installed within 6 foot of the outside edge of a bathtub or shower stall. So you need that as a requirement as well. So again, hazards are the same. That's why we went there. Hazards are the same in laundry areas. That's why we went there as well. Just because you have a laundry area and it's other than a dwelling unit, if we had kids dying in the house, they could do the same thing there. So add a new area for GFCI protection. And there's an example. Any of those receptacle outlets are going to have to be GFCI protected, and more often you're probably going to put a circuit breaker in. And in some cases on the three-phase ones, like up to 100 amps, there's no circuit breaker exists for that. There's no circuit breakers. There's no receptacles that exist. So you'll probably have as a shunt trip a circuit breaker, putting a GFCI relay in there, or not shunt trip, a breaker. You usually you pass it through that relay, and we have products for that as well. So we have solutions to solve those problems up to 100 amps, no problems. Get it done. Added new areas around bathtubs and power shower. We talked about that again. Alignment with 210.8a. Hazards are the same. All right. They don't change just because it's a different type of structure. Crawl spaces. This one generated some. We added in 210.8 a whole separate section E for crawl spaces. Lighting outlets. Now this is lighting outlets. Remember, everything that you've seen in 210.8 has been about receptacle outlets. 210.8e is talking about crawl space lighting outlets. And unfortunately, the problem that we ran across there, it was introduced in the 17 code. We had the case of an electrical worker who backed into a light bulb and was electrocuted in a crawl space. Right. So then the next definition, next question is, what's the definition of a crawl space? Well, you know, we had public inputs for crawl space, and they didn't pass. And what we did was, if you look at the You know, this was what they were proposing. It's an area with a height of less than 6.5 foot. I mean, I thought it was a half decent shot at it, but that was the definition that was proposed. It was rejected, or it was resolved. We don't use the word rejected anymore. We use the word resolved in the public input phase. And that was the panel statement that you see on the screen. We didn't agree that there's a need to define crawl space. You can look at the manual style and check the Webster dictionary for crawl space, and that will help you understand what a crawl space is. And Merriam-Webster says, a shallow, unfinished space beneath the first floor or under the roof of a building, especially for access to plumbing or wiring. Not in the NEC. Again, we fall back to Merriam-Webster. Or if your building code has a definition of a crawl space, that would probably trump what's in the Webster dictionary. And there's our language in D, specific appliances. So this is telling us, unless the GFCI protection is provided in accordance with 422.5 and references 422 for appliances, where the appliance is a vending machine is specified in 422.5. So this is trying to align ourselves with what happened in 422. Remember, 422 says you have to have it in the, they don't say you have to. They give you options in Article 422. Now I have my opinions. I'm not going to deliver them here to you guys, but that's a soapbox I got. But 422 is looking at what they can do from an appliance perspective. We just tried to make changes to align with what 422 and correlate with that. I think both 422.5b and 210.8d still need work in the 2023 cycle. Stay tuned, but this is the language. We're just trying to drive alignment. That if it's in the cord, if you buy an appliance and it has GFCI in the cord or as part of the requirement, then you don't need to put it in the branch circuit. So this is what basically drove that discussion, because how do you make GFCI in the cord accessible when you have things like a Coke or a Pepsi machine or any type of pop machine or soda pop machine, depending upon where you live. It's hard to make that readily accessible, and all GFCIs have to be readily accessible. So that's a challenge. So readily accessible, again, that's the challenge for that. Equipment requiring services, so 210.8e, this is an area where we made some recent changes in the 2020 cycle. GFCI protection shall be provided for the receptacles required by 210.63. And if you think about it, what we did there was we just said, you know, there is equipment that, a lot of this equipment is probably in a basement, which already requires GFCI protection. It might be outside, which already requires GFCI protection. But there are areas where we have equipment that is not in an area that already requires GFCI, and we want to provide safety for our electrical worker. So 210.63 saw some changes as well. We restructured 210.63. I think it reads a lot better, and you'll want to look at that. It's not necessarily related to GFCIs, but it's related to usability and accuracy. You'll want to check out 210.63. Refresh yourself there. So here's an example of a receptacle that is servicing this equipment that if you call it a crawl space, okay, yeah, I could say that attic is a crawl space and I need the GFCI protection, and I probably would need GFCI protection on that light that's there too. But if it's not called a crawl space, doesn't meet that definition, that receptacle, it's in the attic, it still would require GFCI protection. Hopefully that's clear. Now, this was another big change. I think that this one here is really getting a lot of debate in the code adoption process across the country. Outdoor outlets expanded in protection. So we said outdoor outlets, not receptacle outlets. So if I have an outlet, like for example, on this air conditioning unit, this air handling unit, that little disconnect there is wired up through an outlet. That outlet is going to have to be GFCI protected. And so unfortunately, this was driven by a death. That's it's a young man was coming home, wanted to beat curfew, jumped over a fence, and he was electrocuted. And it wasn't because the equipment failed. It was wired incorrectly. So GFCIs are not there for when things go right. GFCIs are there to, if you miswire something, GFCIs and AFCIs are unforgiving technologies. If you miswire something, it's going to catch it. If it fails, it's going to catch it. So GFCI is an unforgiving technology. That is an outlet that serves that equipment. This is a lighting outlet, and it's identified as a lighting outlet, and because I put a light in it, but it's the standard outlet, but it's meant for a light. This is the picture of where the accident occurred. So this change was driven because the child jumped over that little portion of fence, and he came in contact with that air handling unit, or that condensing unit, and was electrocuted. And there's no reason for that. So we have technology, and it's expanded. I know that's going to get debate across the country. There's debate on whether or not there's leakage currents in these devices. Often that's a dedicated circuit anyway. And if you're exceeding 4 to 6 milliamps on a dedicated circuit, you've got a problem. It's going somewhere outside of the normal path. That is 210.8 requirements for GFCIs. We are at 145. I'm going to I'm going to take a real quick look at the chat stuff going on here. There's some delays. I've been, sorry, Arlen. I'm sorry about that, buddy. Just I'm a one-man band. Single outlet on a fridge. We already talked about that. We talked about, okay, so there's nothing. Leakage current is much lower in modern appliances. Absolutely correct, Richard. Absolutely right. And muscle attraction, can muscle even react in less than a half of a second, 0.5 second? Good question. I haven't looked at those charts again. I'm not sure the answer to that one, James. All right, so look at the chat on WebEx. Okay, there's the I hear yous. I was picking on Joe Fellow. Dave Englehart, laundry. David, I believe this was told that it was happening because equal leakage. Okay, so laundry tray. So Don Gannier, thank you. Laundry tray definition is a fixed tub as of slate, earthenware, soapstone, enameled iron, or porcelain with running water and drain pipe for washing clothes and other household linens, called also a set tub. So there we go. So a laundry tray, I always thought a laundry tray was that thing that was under the washer, in case you had a leak and it would catch all that water leaking. But that is not the case. The definition of a laundry tray is that tub, the basin that you would drain that water into. Thank you, Don Gannier. Another good man. A lot of good people in our electrical industry. Marinas. Now, Lucas Ritz turned me on to Marinas. And Joe Fellow, I don't know if he's on the line, but Joe Fellow came to me one day with Lucas Ritz's story, and he said, Tom, we work in codes and standards. We need to fix this. And I told Joe, I'll work on the language, you work on the substantiation. He had the easier job, unfortunately. Lucas Ritz was the stimulus for my my adventure into marinas. There's his story. He was killed in a marina. If you Google his name, you'll find his story. You'll find his father and his mother talking about his story. We lose too many kids in and around marinas every year. This is Noah Winstead. Depending upon what state you're in, you may have heard of the Noah Winstead Act. Unfortunately, whenever a state loses a child, in some cases, they change legislation and try to address the codes and standards in and around marinas. Michael Nudstead. Here's another one. Jumped into the water, and he was electrocuted. 18-year-old. This was the public input back in the 11th cycle. Joseph Fellow. We started this journey with GFCI protection. We said the main overcurrent protected device which feeds the building shall have GFCI protection. And then we said, well, if you do it in all of the individual feeders, then you don't need it in the main. We had the substantiation. We had a whole bunch of deaths associated with this, and it was rejected. And this is a good case to help you understand you can make a difference. The panel statement said, although the recommendation has merit, additional technical substantiation and product development is needed because they were worried about leakage current in marinas. And Joe came back to me and he said, boy, that's a bummer. We didn't get it. So what do we do now? And I said, Joe, that first sentence is huge. He said, the panel said that the recommendation had merit. So we needed to go back and sharpen our pencil. And then we came back and we said, okay, guys, if you didn't like 4 to 6 milliamps, let's take the amp up to 100 milliamps. We said the main overcurrent protective device, which feeds the floating structure, shall have a ground fault protection not exceed 100 milliamps. And oh, by the way, you can put ground fault protection of each individual branch or feeder circuit as a suitable alternative and not required on the main. And then it passed. There were 9 eligible to vote and 9 affirmatives. And that's how the journey in Article 555 with marinas began, because of this change, we had research from the Research Foundation. We've had multiple public inputs. We basically stirred the pot, and I believe that marinas are much safer because of that. And it was because Joe Fellow came up to me one day and said, how do we change this? Anybody can do that. Anybody can make a public input. When you see something that doesn't make sense, knowing electricity like you do, make the public input, and you can be an institutor or a driver of electrical safety. This is the language that we had in the 2011 cycle. This was the Research Foundation that was published afterwards, and everybody complained about the 100 milliamps. And then what the Research Foundation came back and said, you know what? We need to change that 100 milliamps. We're going to change it down to 30 milliamps. And then in the 17 cycle, they changed it and said that all overcurrent protective devices that supply the marina have to have 30 milliamp protection. And then that became a little bit of a challenge because of leakage currents issues. And we made some changes in the 20 cycle, and there was a TIA that was put together. And we made some change after the fact, and we made that work. But this is an example of in a marina that we have that label, and we have ground fault protection instituted in these applications. We have solutions. We can fix that. So in the latest version, we've sort of separated this out in the 2020 version. We have receptacles. The receptacles have to have GFCI protection for personnel. And then shore power has to have 30 milliamp protection, and any of the feeders have to have 1,000 or 100 milliamp protection. So we made a lot of great things to change in and around marinas. And I think there's some lessons to learn about how we staggered this protection. We have 100 milliamps feeding so that the added leakage currents, it gives you some breathing room on leakage currents, which should be low anyway, but the 100 milliamp threshold gives you some leakage, some breathing room. And then the point of use, the receptacle outlets for that you would be plugging in appliances, 4 to 6 milliamp, your 15, 20 amp circuits. And then anything that's plugging in a boat, we're at 30 milliamps. I think that's a really good solution. So any of the shore power pedestals, those are going to now have 30 milliamps when it's going to power the shore, and it's going to have 4 to 6 milliamps. And if you ever go out to a marina and look at the condition of some of this equipment, this is bringing up other concerns on how long does this equipment last? Should there be a lifespan? Should we say you need to replace this equipment after so many years? We do that on smoke detectors in homes. But when you look at the conditions of use and you look at the environments these things are in, yes, they're built to different standards, but I mean, we're throwing these things into very rough conditions. And the shore power, whenever you hear shore power, that's that 30 amp outlet on that pedestal, and everything else is your receptacles. So all 125 volt single phase 15 to 20 amp receptacles have to have ground fault GFCI protection. So when you see that word GFCI, there's your GFCI, And again, it's not meant for shore power. And actually, that picture that you're looking at right there is an illegal installation. You're not allowed to do that anymore. Or depending on where you're at, you could put a receptacle out there, but depending on what it's being used for. So there you notice this receptacle has a label, not for shore power. That's a key. That is for you're working on that marina on the dock, not for shore power. I learned what a dirt dauber during that inspection. So feeders and branch circuits, again, that's where your 100 milliamp is in marinas these days. You're at 100 milliamps going out to a feeder. You know, we're allowed to put transformers out there. There's nothing that says you can't put a transformer on a boat dock, floating dock. But those feeders are going to have GFPE protection at 100 milliamps. You know, those feeders that go out there, they're all going to have 100 milliamp GFPE protection. These are the types of devices that you'll see given GFPE protection. Leakage current. So the other thing they said was, you know, they want to have temporary places where you bring a boat in. They want to be able to test that boat before they plug into the rest of the marina. So we created some language where you have more than 3 receptacles supplying shore power to boats. A leakage current measurement device has to be available and used to determine leakage current from each of those boats. Again, you want to avoid the unwanted tripping issues. And then there's an informational note in there in 555. Again, there's these are just informational notes. So that marina has more than 3 shore powers. That's going to need to have it's going to have GFPE out to that, and it's going to have that temporary, that portable device. All right, I got through marinas. I didn't think I was going to get through that. And I am going to, as I look through the chat session here, I'm going to display the last slide for our viewing audience to, if you were interested in taking the quiz for purposes of PDH certificates, which I'm still working on from yesterday. This use this code MENTI at 2280180. Please do that now, so I can just make sure that that's happening. We are at 157. I'm going to look at as I call this up, I'm going to look at the chat sessions too. And I'm on 2020. Can't believe it's GFCI PDH. I don't know if I have your name. Hold on, let me just make sure that I have the requirement for you to put your name in there and email. Yes, I have your information. Okay, so hopefully, yep, looks like people are downloading and putting their information in. Okay, so let's look at the chats. Thank you, Don Gannier, for the definition of a laundry tray. And Edward, on equipment like dryers, washers, refrigerators, others, would it be more effective to mandate manufacturers to provide these machines with embedded tamper-proof GFCIs? Okay, so here's the thing. This was the really interesting part about when that appliance manufacturer came to panel 2. They tried that, and they tried to make that change in the standard, and it did not pass the standard. And that's why they came to code making panel 2, as they said, look, we want it in the appliance. We want to change the standard, because here's what happens. It's just like if you're building a home. If you're going to quote a job on a project, you don't want to be the guy providing all of these additional things that aren't required by code and then lose the order because you've added more cost to the solution. So that's what was happening with these appliance manufacturers, saying we can't change the standard. We tried, and it really. And if I have an old appliance, and my dryers and my washing machine came with me from my other house, they were built to a standard where they didn't have GFCI protection built in, even if the new standards required it. That presents a hazard in new homes. So the requirement in 208, now I'm going to get on my soapbox, the requirement in 210.8 is there so that if I bring old appliances, I bring anything that is an older product, newer product that doesn't have GFCI protection, it's going to be afforded protection. 422 influences the standards, and that did not that will drive the standards. But if I do have GFCI in new products, I don't have it in the old products, which I can bring to new homes. So, and it's just the debate. Do you need it in the branch circuit? Do you need it in the appliance, or do you just put it in both? We are experiencing on equipment. Where's the we are experiencing? We are experiencing issues with commercial kitchen installs, installing of equipment with detached plugs onto a three-phase receptacles. EC claims it is all wired. Electrical contractor claims it all is wired into shunt trip of hood. We do not see that as compliant. One issue, though, okay, so from a compliance perspective, whatever the solution there is that's meeting the 210.8b requirements, they have to be listed. That's why the standards are very important. If it's listed as a GFCI solution, then you could argue it is meeting the requirements of 210.8b2. This doesn't, I agree with you, it doesn't sound like it is meeting that requirement, but you would have to ask for, show me what it's listed for, get the label off the equipment. If it's listed as a GFCI, then it would meet the requirements for 210.8b. If it's not listed as a GFCI, it will not meet the requirement. One issue, though, we are understanding that there are no three-phase GFCI receptacles. Right, there's no GFCI receptacle. There's limited availability of GFCI circuit breakers because above a certain amp value, I can't put all that stuff into a small device, so you use a relay. And there are some attractive solutions that you could mount right next to that equipment. You can mount that back at the panel board, and you just wire it in series with that appliance, and you'll provide that protection. We do have solutions for that. Reach out to your local Eaton sales individuals. Your application engineer should be able to direct you to the Eaton solutions to help you with that. Not the countertop next to the sink, a food prep area. Yeah. That I would argue that is a food prep area. Yes. Definition of crawl space: a shallow, unfinished base space beneath the first floor or under the roof of a building, especially for access to plumbing or wiring. Thank you, sir. Thank you. For a Lynn Thomas, for a boat dock panel, should the feeder have ground fault breaker in addition to the individual receptacle outlets? Remember, it does. If you have the feeder going out, needs to have at least 100 milliamps. Once you get the feeder out to the boat dock, then you go to the pedestal, or maybe that feeder goes to the pedestal. That pedestal would be protected with 100 milliamps. The shore power, that 30 amp outlet that goes to the boat, is going to be protected by 30 milliamps. So there'd be a little GFCI breaker GFPE breaker in there. And then the receptacle will be protected by 4 to 6 milliamp GFCI. Okay. Oops, wrong recipient. Sorry, Tom. It's okay, Nihad. Require that equipment has to be made with stainless steel. Ooh, that's a good one. The shall be used aspect of the rule is a fuzzy concept. Who enforces it? Not sure exactly what they're referencing there. It can be fiberglass. Look, I'm glad the dialogue is going on. That's where we learn. Great job. Check with the local and state officials for exceptions to GFCI. Yeah, so there are some states. I know Ohio had an exception for sump pumps. Local, that doesn't mean you can't put it on there. And some appliances will say you have to put it on GFCI. So remember that. The boat leakage test enforcement. Got it, David. Yeah, it's really hard to enforce a portable unit. I agree with you 100%. That's a challenge for enforcement. Absolutely. All right. Well, it's 2:03. Some pumps that are cord connected have a leakage current test. Beautiful. 100 milliamps. I agree, Robert Victoria. 100 milliamps is still pretty good protection. I hope that our web system was good. I think we had good performance. I didn't see any of the yellow bars come up. Let's look and see. Mathur Abbasi, all of the codes in New York City are reactive, not proactive. Yep, unfortunately. From what I read, the only device that meets the NEC definition of GFCI is a class. Absolutely, Ryan. Very important point. 680 and 422 specify Class A? Do you see these changes as necessary? So what they did in 680 and 422, they're really driving it home that it has to be a Class A device. And I think anywhere you use the term ground fault circuit interrupter, you're into a Class A device based on the definition. I don't really need to clarify that anywhere else unless there's a need. People are confused with it. I personally have experienced people use the word ground fault protection, GFI, interchangeably, and that's a challenge for a lot of individuals. But again, leakage current is much lower. Anywhere we can drive the clarity that's a Class A device is important. I don't know if it was absolutely necessary, but I don't think it can hurt. Okay. Well, I looked through all of these. I hope the YouTube was good. And I want to thank everybody for dialing in. I want to thank everybody for watching. I'm enjoying these as I practice my social distancing. And you never know, some of this might continue. I thank you for Ryan Jackson for dialing in as well. And Don Gannier, you would not believe the knowledgeable people that we have on this call. Jeff Fecteau from Underwriters Laboratory. We've got Mather Abbasi from New York, who's right on the front lines of all of this stuff. We've got a lot of really good, smart individuals out there that are dialing into this, and I really appreciate that, and sharing your knowledge either on the chat. And I'm trying to regurgitate what's on the chat for those on YouTube, because I know you don't have access to the WebEx chatting. Thank you. I'm going to sign off now. I appreciate everybody's participation, and stay safe. And we'll see you tomorrow. We're talking about arc fault circuit interrupt. Okay, I'm gonna stop the streaming on this side.